All right. So, welcome back. It's hard to believe it's February already, but it is. You'd actually think it was June or something, given how nice it is out. But if you remember from last time, all right, settle down. We were talking about processes and the user level interface to them. And one of the things we talked about was both fork and wait. And I just wanted to very quickly put these up. So the idea behind fork is fork creates a duplicate of the current process, the parent process, as a child. Wait is the way that the parent now waits for the child to exit. So this is a good example of some code here, which we execute fork. And after the fork, and in fact, right after the fork, what happens is we have suddenly two identical processes, one of which is the parent, one of which is the child. And the amusing part about this is the fork system call returns with different values depending on whether you're the parent or the child. If you're in the parent, you get back the PID of the child that was just created. If you're in the child, you just get back 0. If there was an error, you get back a negative, which I haven't shown here. So notice that here, when the return value from fork is greater than 0, we're the parent, so the parent is running this code. It actually goes ahead and gets its own PID and then kind of says, basically says, hi, I'm the parent of this child. And then wait is a system call that says wait for the next child to exit. And when that happens, it sets the status into this integer variable here, status, and returns the PID of the child that just exited. On the other hand, the different branch here, if the CPID is 0, we're in the child, and at this point the child gets its own PID and says, hi, here's my PID. Were there any questions on this? That made sense to everybody? Now, one thing that's kind of interesting is when I say duplicate the state, I really mean duplicate the state. What we're going to see later in the lecture is you actually get all of the file descriptors, etc. So suddenly you have open files, and both the parent and the child have open file descriptors for the files they opened. Okay, so really it is a duplicate process. Okay, good. Now, by the way, there's a whole bunch of different versions of wait. You can actually wait for a specific child to exit. You can say, return quickly if nobody's ready to exit. But this basic version here is actually blocking, so the parent will go to sleep on this wait call until it comes back. So the other thing we started to talk about, and we went through very quickly, so we're going to be a little more careful this time, was we started to talk about the system call interface and how it's what is often called a narrow waist. Okay, this is somebody who's been dieting a lot, I guess, and lifting weights. And what you see here is everything goes through the system call interface. So the system call interface divides the user level code from the kernel code, and immediately on top of this is typically a whole bunch of libraries like the C library, and then here are all your things up top, your applications, and then below this is the kernel and hardware, okay? So this is where we're starting to talk right now, and what you're doing with your first couple of homeworks, actually homework starting with homework 1, is you're programming above the system call interface. As soon as we start getting into the actual group projects, which is going to be very shortly, you're going to be programming below the system call interface, okay? So we're trying to give you a flavor above so that you understand when you go below. Now, the other thing we started to talk about was that this I/O interface, which is one of the marks of Unix, is how everything is looked at as a file. Okay? Device operations look like files. File operations, not surprisingly, look like files. Networking operations look like files. We're going to be showing you that in a moment. So everything has been made to look like a file. And so that's something to keep in mind, and you're really going to see this as we get later in the lecture today. We also talked about, as a result of this view, we always open the thing we're going to use before we use it. It's byte-oriented, okay, which means everything is about reading and writing bytes, which are how many bits? 8. Okay. How many bits is a bit? Good. You guys are with me today. Good. The kernel typically does all sorts of device-specific buffering, but then when you use the streaming version of I/O, you can have the user level does buffering as well. And the buffering that the kernel does in the read side is for performance, so it buffers blocks off the disk, and maybe you can read them 1 byte at a time. The write on the other side is something to always keep in mind. When I write some data to a file, it may still be in memory in the kernel and not on disk. So just because I did a write system call doesn't mean the data is permanent, and you have to make sure that you do the right sort of flushing and syncing to make this work. Okay. Now, and you close it also. So we had a bunch of storage layers we also started talking about here. So we have the application level, of course, but then this file I/O has both a high and a low-level version of it. The sort of streaming or buffered I/O operations all have the letter F in front of them: F open, F close, F read, F write. The lower-level ones don't have the letter F in front of them, like open, close, read, write, okay? So the difference between streaming and non-streaming, there's an F, okay? Remember that. That sounds like a good test on good question in the next midterm. Below this, of course, is the system call interface, and then the file system interface is an interesting one, which we're just going to touch on briefly, but you can have many different file systems. You can have NTFS. You can have various flavors of EXT, 3, 4, whatever. And there is actually a whole layer inside of the kernel, depending on what file system you've got. And then below that is the actual device drivers, which deal with the fact that you might be using USB sticks or disks or whatever. So all of these things kind of work in concert so that the application doesn't have to worry about this. So a lot of what we talk about in this class is about how to put abstractions together in a way that's secure, convenient, high-performing, so the application writer doesn't have to worry. Okay, so you guys are helping to design the plumbing and the high-quality infrastructure so that application writers do a good job. Okay? So the file system abstraction, the high-level idea with the basic file system in the actual files are basically that files live in a hierarchical namespace of file names. Okay? So those files are essentially just a name collection of data in the file system. So the file data can be formatted any way you want, and the operating system at this level doesn't care. Doesn't care if you've got binary data or text data or whatever. The application is the one that interprets it. Now, this is a little different from other operating systems out there where the operating system has some knowledge of the format of the data. In Unix, typically the data is just unformatted bytes. Okay. And then as far as the namespace is concerned, we talked about directories and paths. I'm assuming everybody is very familiar with paths. Do I have to go into this again? I just wanted to briefly mention it, right? /home, /ff, /whatever. This is a way of identifying a particular file in that namespace. So this is the namespace. Question, yeah? What's a linearized object? Well, that depends a lot on context. What's the context? In that context, so in that case, what happens if you have an object-oriented language like Java or pick your favorite one? Objects are these complicated collection of pointers and structures and what have you. When you want to write it to disk, you've got to do what's called linearizing or serializing is probably a better term for that, where you actually turn it into a stream of bytes which can go out on the disk, and then when you do it the other direction, it's the reverse. So actually, I should fix that to say serialized. I don't know if that would have helped either, but that's what that means there. Good question. Okay, so so the high-level streaming API is things with an F in front of them. So F open, F closed. It treats the files as a sequence of bytes. When you do an F open, you give the file name to open, and then you have a bunch of modes, which are actually a string. And those strings can be things like W plus to open for reading and writing, truncating to 0, etc. Okay? So this F open and F close are the important ones. Now, of course, you want to remember F flush to make sure that you push things at least down into the kernel when you're done. But were there any questions on this? Okay, so you always have to open before you use. I'll show you an example in a second. A little bit more about the namespace here. So typically every process has a working directory as well. And so that means that although you could specify /home/ff/cs152 or whatever, in fact, since it has a current working directory, you can actually eliminate having to put the current working directory there and just use a piece of a path name like index.html. If there is no / at the very beginning, then what you're really saying is do this relative to the current working directory. And this includes things like .. /index.html, which really says take the current working directory, go up one level, and put index.html in that. Okay? Everybody's seen that syntax before? Okay, and that's usually the cd command, right? Change directory is actually changing the working directory of the shell. Okay, but all processes have one. So standard streams, we mentioned this last time very briefly. Sorry if this seems like repetition. I just wanted to make sure that we didn't go through it too fast. But there are some predefined streams that are defined for every process. They're standard in, standard out, and standard error. And these streams are basically, if you don't do anything else, the console input, output, and basically the console output, but for errors. And so if you don't do anything, incidentally, standard out and standard error are kind of intermixed together going out on the screen, but they are things that you can separately deal with. And this leads, of course, to things like pipes, which are really ways of connecting the standard in and standard out of each of these processes. Okay? Everybody with me on that, right? Good. Now, very quickly, we showed this last time. I didn't really go through it, but there's a whole bunch of things that start with F, which are streaming things, right? F put C, puts a character on a file. And notice that these things are all of the form. Here is the file that you've previously opened with F open, and then here's the thing you're putting. So this is putting a character, which is a single integer. This is putting a string, etc. There are things to get a character off the keyboard or out of the file, to get a character, to get a whole string, etc. These are all F functions, which are things to get used to. Okay, what's the way that you find out how they work? The man command, M-A-N for manual, right? So you can say man F put C on a Unix system, and it'll tell you what F put C is in terms of its inputs and outputs and behavior. Okay? Interesting things that you're going to want to learn to love or hate are things like fprintf, where actually what you're doing is putting formatting together to produce an output that's formatted a certain way. So that's one you should really look up. Okay? If you don't know how to use fprintf, you should look it up. Okay. So here's an example. Thought I'd throw this out here. So here, we've all learned how to love C by now, right? You guys all love C. Oops, I heard somebody who was so enthusiastic they couldn't contain themselves. But here's an example of using some of these things. So, typically speaking, we use sharp defines for things like length. So this is 256 characters. I make a buffer. My buffer has 256 characters in it, and then I use that later. And you can see in this particular function, I open a file, okay, and this out file is a file star. All right, and so once I've opened this, if it returns a null version, then I've got an error. Otherwise, I go in some loop, which gets the next string. Basically, when I get a return from this, it's either null or its length is 0. I'm totally done, and I close the file. Otherwise, I take the result, write it to my output and continue. And so notice that what I've done here is I'm reading from standard in, and I'm writing to the file that I opened. Okay, so this is just boring sort of code, but it's the kind of bread and butter code that you should be very comfortable with. Okay, it's just, this is how you use those functions. Okay, this does not compute the last digit of pi. I'll show you that code later in the term, much later. Questions? Okay, so one thing to keep in mind, and this is just, was a question? No? So one thing to point out, by the way, is every function has a return that is either returning a good result or an error. Get familiar with that. Normally, an error is a negative return if your returned value is an integer, negative. On the other hand, if your return value is a pointer or something, errors are often things like returning a null pointer, which is 0. Okay, so to always be aware of what the return values are. Okay? Why should we always be aware of return values? What's the negative consequence of not dealing with a return value properly? Yeah. Well, here's a good example. What if fgetS, returns a null string, and then I try to put in a null string? I probably end up with some sort of seg fault or something bad. Okay. Worse is you have some code that people are relying on, and as a result of not checking an error condition, somebody figures out how to breach your code from a security standpoint, and they steal a bunch of credit cards or something. Okay, so always be aware. It's very easy to not check errors, but if you assume that errors never happen, they will. Okay, that's the karma of Unix. Errors happen when you least expect it. Okay, so there is a bunch of other things here, by the way. Positioning commands that let you seek to a particular offset, and so you can go back and forth in streams, and you can rewind to the beginning and so on. Okay? Good. Yeah, question? Yeah, so that's a really good question. So here I'm f-putting, okay, as opposed to being off-putting, right? So I'm f-putting onto that file, and the question is, when does that make it to disk? Well, it sure doesn't right away, because every command with an F actually buffers at user level. Okay, so they're not even in the kernel yet. So when I do an f-put-f, it's quite possible that this is just in some buffer in the C library and hasn't made it cross a system call. Okay? So what I can do is I can do an f-flush, which pushes it at least out of user level into the kernel. But even then, you're not sure it's on disk because the kernel is doing its own buffering commands. Okay? And so that you have to start doing things like sync and some of those to really make sure it's pushed out. Okay? Very good question. And it's tricky. And every file system type actually has a slightly different heuristic as to when it flushes to disk. Yeah?
So, but the kernel it has to keep a queue of them so that way they're all arrive in the correct order when they're actually written, though, right?
Well, that's a good question, too. So, in fact, the basic view of the kernel that is, unless we start talking about a multiprocessor where things are on different nodes, and we're going to get to networking in just a little bit, the kernel, as long as it buffers things in a way where all of its writes, maybe they're in memory, maybe they're on disk, but as long as reads show you the last write, then there's no way for the process that's running, any process that's running on that particular physical machine to know the difference as to whether it's gone out to disk or not. Okay, so the kernel tries to preserve ordering in that instance, even while it's playing with deciding which block goes to disk and when. Okay? Where this starts becoming visible is when you've got multiple machines and there's some networking and remote file systems, and then all bets are off. And we'll have some fun talking about that kind of stuff in a few weeks or whatever. But that's a great question. So it's kind of, as long as I can fake out everybody that's coming through the system call level, it doesn't matter what order I put things on disk until we crash, and then you got mess, right? Because if I crash and I put things out of order on the disk and I don't keep a log or something like that, then recovering could be a real mess. Great question. Okay, you guys are all setting me up very well for later lectures. Any other questions here? By the way, since we're on this topic, it is kind of interesting that 10 years ago or whatever, they started building disk drives that had a lot of buffering in them, somewhere 10, 15 years ago, on the hardware. And file system writers weren't quite up to speed on that, and so they thought they were being really good about ordering and pushing things out to the disk in order. But the disk itself was reordering and keeping things in its own RAM memory. So there were failure modes where the power would go out in the wrong place, and the kernel was convinced that it had stored the log in the right order on the disk, and in fact, they'd come back and the log would be screwed up, and that was because the disk drive itself was doing stuff the operating system was not aware of. Yes, isn't this fun? Okay. So I don't really have a lot of new administrivia. You're all aware that we had drop date on Friday, so all of you are mine for the rest of the term. I will point out that a few of you, I did get somebody say, well, I was at office hours and you didn't come there today. And I will tell you that what happens is oftentimes I get stuck in meetings that operate on Berkeley time. So wait until at least 1:10 before you decide that I'm missing in action. I was actually there today. I apologize for people that might have come a little early. Homework 0 is due today. That you should know. Homework 1 is handed out today, so get moving. These are all, homework 1 is really going to let you start doing some shell programming, and you get to really do this high-level interface that we've been talking about. So this will be good experience. Get to know your TA. Last time I said I would try to find out whether I could create a new Thursday section, and it didn't happen because it turns out that there are some deadlines on when I can get new rooms. So I guess we're stuck with the sections we've got. So those of you that are in overloaded sections, there are some really nice sections where you can get to know your TAs extremely well on Friday morning. So you might consider the Friday morning sections. I know for a fact that Friday morning is when lots of learning happens. So, oops, my bad here. Sorry. Okay, so we're going to actually have group sign-ups this week. I don't have the forms yet or whatever, but I'm sure they will be out on Piazza as soon as they're ready to go. But we have some TAs that are busy shaking their heads. But we're going for 4 people in a group. Okay? We don't want, no, 5 is right out. This is like thou shalt get to 4 by passing through 3, and 5 is right out, right? 3 is something that we will agree to only under duress. So try to get 4 people in your group. Okay? Talk to us one way or another if there's a problem. And then finals conflict, I won't go into this, but make sure you let us know about conflicts. So far I only have 1 conflict I know about that's not a class overlapping related conflict. So if there are any others, let me know. Okay, that's my administrivia for today, which is stuff you've all heard before. Any questions? Nothing too exciting, other than, wow, you're on to homework 1. I know, I'm excited. How many people have ever programmed using the shell before? A few of you? Okay. Good. It's a good experience. Do you like this idea of learning the user level stuff first so that when you start diving into the kernel, you get a good handle on what's going on? I actually, we've done in the past 162, we used to not do that, and I think people got a little lost sometimes because it's sort of like, well, I'm implementing mechanism, but I have no idea how it was going to be used in the first place. So I think this is a good good entry into what we're doing. So let's go a little bit more below the surface, and this is where I was going really too fast last time, so I did want to be a little bit more careful. So we've been talking about all the functions with F. Now let's talk about it. There are functions without F. So if you look, you'll actually find things like open and close, and create is actually kind of open with certain modes, so that's a kind of a macro almost, syntactic sugar. But these are all system calls. These are direct system calls. The things with F's are library calls. These are actual system calls. So if you went and you did a man open, you'd find it's in manual section 2, which is where the system calls are. So these are actual things that cross that boundary into the kernel. Okay? And so among other things, for instance, when you open a file, you have to put in a bit vector of what access modes you want, flags, and so on. But notice this is an integer. So this is not a string. This is a bunch of ORed together flags. And then also, there's a bit vector of what your permissions are that you want for creating these files. Okay? What I did want to point out here is notice the return value here is an int, not a file star. So these are just regular integers starting with 0 that represent the open file descriptor, and they are the actual interface between the kernel and the user as to which files are open. Okay? And so in particular, standard in, standard out, and standard error are actual, have file descriptor 0, 1, and 2. Okay, those are always taken. So there's a lot of weird stuff you can do about closing file descriptor 1 and reopening it or duplicating it or whatever. These are things that are pretty poorly abstracted, but if you ever see somebody doing things with descriptors 0, 1, and 2, you can think that they might be doing some magic with standard in, standard out, standard error. All right? But be very careful because basically, as I mentioned before, streams are on top in the library. The file descriptors are underneath. Don't cross over if you can avoid it. Try not to mix them up. Okay? They're a file that's open with fopen and a file that's open with open. They're at different levels of the library. So you don't want to open the file with fopen and try to do a read or write on it because there's no way to match those up. All right? A file star is not an integer and vice versa. Okay, and this is just kind of dumb to say, but I thought I would say that. But notice that read, write, lseek, these are actually system calls. And notice the first parameter typically is always an integer file descriptor. So you've done an open, it got back the file descriptor. Here, you did an open, you got back the file descriptor, and then you put it into a read or a write to do the actual read or write. And I didn't mention on this, there is this thing called fdopen, which lets you take an open file descriptor and turn it into a file star if you feel so inclined. So you can do that. You can abstract a file descriptor into a file star. Okay. And we could easily talk way too much about this stuff, so I don't want to. But notice, here's some important things like fsync and sync. This is how we get stuff out to the disk, okay? At least push to the disk. Whether the disk actually writes it on its own spinning media is a whole other story. Yeah, question. It's a good question. Every process actually, in principle, has its own file descriptor space. Okay, so 0 in process A is different from 0 in process 1 or process B. And when you think about it, that makes sense because each of them can have their own input standard in. Especially when you put them in a pipe, everyone's got a different standard in. They've got the standard in, which is the standard out of the previous process there. So the file descriptor space is unique per process. Okay? All right. Unless, of course, you do a fork, in which case they start out with copies of the same file descriptor space. So from that point, the numbers match, but any new opens or closes are not going to track between the two of them. Okay? And we'll actually show an example of doing that in a little bit. And so there's lots of system calls that are much more direct and things that the libraries typically use, and so we're not going to go into all of this stuff, but there are ways of getting asynchronous I/O and duplicating file descriptors. So this is a way to get two file descriptors that refer to the same file and so on. Lots of interesting things, and we're not going to go into them right now, but I just want, if you're feeling so inclined, you can start reading through some of the man pages for different types of system calls. Yeah, question?
For the open call, is the integer actually the file descriptor?
Yes. The integer, it's an integer, and it's the file descriptor. Yeah. So file descriptors are integers, as opposed to file stars, which are actual pointers to structures. So, good question. And you see here, so this is a great example of why some people think C is such an awful language, right? So what we're putting in here are file descriptors, which are things referring to files that are opened, and yet we just call them ints, right? I mean, that's a kind of horrible, most of our language colleagues in Soda Hall on the 7th floor cringe whenever they see code like this, right? Because it's just awful. But it's c'est la vie. Okay. Well, you know what? I have to say C is C. What can you say? I'm not a big fan of that either, but it's kind of what we've got to work with. So here's a great example of using these low-level functions. So, here's a case where we come in, and we don't have to open the standard out or standard in macros because those file descriptors 0, 1, and 2 are always there when we start up. So here we're writing to this, and we're saying I am a process, and notice this string has exactly 16 characters, and so we write those 16 characters. Here we're reading into a buffer of maximum buffer size. Here we're actually formatting an output no bigger than the buffer, and so on. Okay. I don't want to go into this in detail. Questions? Okay. So now let's go a little further below the surface. The system call interface is humongous. I mentioned last time how Linux has a huge number of system calls, which tend to be a union of a bunch of other ones. But ultimately, the system calls are numbered, and those numbers represent a table which, when you make a system call, what happens is we make a control entrance into the kernel, and it looks up an entry point and actually goes to a well-defined point in the kernel. Okay, and that's how we contain our control. And there are classes. We had an advanced OS class which gets taught every now and then where you're actually extending this table. Actually, do we extend this table in lab? We don't extend the table, do we? The system call table? No. Yeah, so we definitely do this in more advanced classes. But so anyway, so if we go a little further, notice that we had file descriptor numbers up here. Where are they being stored? They're being stored in the file system themselves. And so if you look internally, there is a file structure which represents that file you've opened. And you can look in this, and it's got a lot of interesting things, including, and this is inside the kernel, by the way, so it includes things like, where's what I'm looking for here? Lots of different operations, including ones that have to do with what file system you're using. And so if you look a little carefully, here we've got things like this, which this is when you go to do a read or a write, inside the kernel, it actually calls VFS read, which is the virtual file system. And inside that VFS read, it gets the file descriptor that's inside the kernel for a given file, and it calls and does a bunch of checks. And notice here that file descriptor has file indirection fop, indirection read. So what is this? This actually says for the given file you've opened, look at the table of possible operations on that particular file system and pull out the read. So that was what I was looking for here. Why can't I find it in here? I had this earlier today. Anyway, you'll have to trust. Oh, there it is. Constant structure file operation pointer fop. That means that Whenever you open a file, the kernel figures out what type of a file system is it, hooks you up with the operations for that type of file. If you've got an NTFS file or you've got an ext3, there's a different FOPS pointer in there, and that means that then when we go to actually do the VFS read, the right thing happens. Look at that abstraction. That's a bunch of abstraction in the kernel to allow you to basically have lots of different file systems. How many people have heard of ext3? What is that? One of the basic Linux file systems. ext4. Okay, newer one. NTFS, Windows, right? So all of these different types of file systems can be represented in the same kernel based on which file system you open from, and they sort of control the ops. And then if you actually look at the file ops structure, when we start getting a little more in the kernel, you can look at it, and look, there's a whole bunch of pointers to functions, another fun C aspect, which tells the VFS layer how to do the file operations on that type of file system. Okay, and so the VFS layer allows there to be a whole bunch of different file operations for different file system types, and so none of that has to be exposed to the user, certainly, and it doesn't even have to be exposed to the higher levels of the operating system. Okay, are there any questions on that? In the Advanced OS class, sometimes we actually implement a unique type of file system, and we build your operation structure and link it into the VFS layer. Okay. So then finally, we talked about device drivers. This is the very lowest level. So this is file system level, but the file system uses a disk drive. So somewhere there's a device driver for the disk drive, and this is device-specific code for that particular disk drive. And it has two halves, top half and bottom half. The top half is the part that's close to the user, and when you go to do a read, you go to sleep in the top half. The bottom half is close to the hardware, and that's where interrupts run. And so the device driver actually has two levels. Unless, of course, you're in Linux, which reverses these two, and the top and the bottom half are different in Linux. But for now, we're going to do it this way, okay? Because every other operating system has this assignment. And so these open-close read-writes are different from the previous one. These are about opening the actual physical device. These other ones are about the file system. These are about the device, okay? Lots of layers of abstraction. And of course, if you actually look at what happens with a device driver, this is kind of interesting. The user program requests some I.O. We go into the kernel I.O. subsystem. It says, do I already have this in my buffer? If so, I just go ahead and return the data. Otherwise, I go down and send the request to the top half of the device driver. The top half of the device driver starts the operation and then puts the process to sleep. Sometime later, we get an interrupt. We read it off the disk drive, put it back in memory, transfer it, wake up the process, go back to the kernel I.O. subsystem, and go back out. And so this is part of what's transparent to you as well. You don't actually worry about this unless you're designing an operating system. Okay, so this is kind of interesting that this all works properly. It does. Okay, but you can start to see why the device subsystem, I hope everybody's getting this flavor, is the thing that causes some of the most trouble with reliability in operating systems. Remember how the first day we talked about how device drivers, are that thing that crashes the most? Here you can see the complexity of trying to make this work properly. Okay, and you don't need to understand all these pieces. I just want you to see kind of the flow. Okay? All right, at the risk of getting too deep in this, are there any questions on this, or do we want to just move on for now? Questions? Anybody feel like they would want to write a device driver someday? Do we have any? We don't have any crazy people in this class. Wow. I haven't inspired you yet. We'll do this later in the term and inspire you. So here's our picture. So now you can kind of see, and this was where I drove our poor transcriber nuts last time. But what happens when you do an fgetc? Well, you're at the highest level. The fgetc is referring to a file star. So you go into the high-level C library. That file star has an associated low-level file descriptor. So the library looks up that file descriptor, does the actual system call, which takes us through the VFS layer into the file system, and the file system calls the appropriate things for the particular type of file, which eventually calls the device driver. You get the data off the disk, and you work your way back up, and the application's really happy because suddenly it has a character. End of story. Okay. Good. So I'm going to change gears a little bit unless we have any questions. So let's go back to this Unix view, which was pretty unique at the time it was first put forth, that everything is a file. Okay? Everything's a file. Files are files. Network communication is a file. Thanksgiving dinner is a file. Okay? Everything's a file. And I guess spring break is where we're going at this term. But that means that when we communicate between two processes, one way to look at that is process A does a write on some file descriptor, which you could say goes into a file, and process B does a read on a similar file descriptor, which has opened the same file, and voila, we just communicated. I wrote it in one file from one process. The other process read from the same file, and now we've just had communication. Okay? Is that pretty easy for everybody to see? One process is writing the file, the other one's reading from the file. And, of course, the producer and consumer are obviously different processes is quite a possibility. And what's even more interesting is we could easily separate this in time, right? So process A could write a bunch of stuff, and then process B could come back tomorrow and read it. Okay, not a big deal. And, but a file like this is not a very efficient way to do things, because what if we're really talking about communication? And we want to write, everything gets written exactly once and read exactly once, then going to the trouble of putting it in an actual file seems a little bit excessive unless I'm really interested in logging, right? I want to know everything that happened in the past. I might do it this way, but pretty much instantaneous communication, you wouldn't want to necessarily do it this way. Okay? But even if this was not actually a file, we can still make our operations look like file I/O. We can do writes and reads, no problem. Okay, even if what's stored here is not a file. Everybody with me? So, suppose we put the internet in the middle, just because we can, right? So here's a cloud, and suppose we write into something, and we read from something, and the bytes magically go from here to here through magic. And as a result, process A, which is here, and process B, which is in Beijing, are communicating with each other. Process A is doing a write to something, and process B is doing a read from something, and now we've got communication going on, but there isn't necessarily a file in the middle, but the interfaces are the same. Okay, and that is basically what happens with internet communication. And what we're going to call these endpoints are going to be sockets pretty soon. Okay, and so this is exactly what a socket-level interface looks like. The mental model you ought to have here is it's just like a file. I'm writing to the file, I'm reading from the file, and I just happen to be distributing this thing, over geographical distance. All right, and basically this is an abstraction for connected queues over the internet, but you start asking the following questions, like what does open mean? Right? I mean, obviously with a file, it's clear what open means. Open means get myself a file descriptor that allows me to tie into all of that mechanism I just told you about to talk to the file. But this is kind of funny. What does open mean? And you might also ask, what's the namespace? For files, it was pretty clear, /home, /users, /Kubatron, /whatever. There's an obvious namespace for files, but what is the namespace for the internet? Anybody want to take a stab at that? What was that? Somebody said, raise your hand. IP addresses seem like a form of namespace. Yes. I'll buy that. What else? I mean, host names, right? www.something.something.something also seems like a namespace that turns into IP addresses, right? So, yes. And, now you sort of start asking the question of how does this thing even hook up? I mean, how do I make sure that two endpoints are connecting with each other the way they're supposed to? So this kind of gets a little interesting here. And we can start talking about clients and servers. And I apologize there that something happened to my animation there. But suppose that we have two items that want to talk to each other, two things, a client and a server. And typically what happens is the client is the thing that's issuing requests, and the server is the thing that's responding to requests. And so the client is going to want to do something like write a request as a buffer. It's going to go into some queue of requests, and then it's going to start waiting for the response. And it may do that immediately by doing a read for waiting for the response. So I do a write, and then I go and do a read, and because there's no response yet, I'm going to go to sleep. It's a very common paradigm. I do a write for the request, and I go to sleep waiting for the response. Okay, and what happens on the server side? Well, it reads from this request queue going this direction, gets the response, or gets the request, decides what to do with it, writes the response back. That response comes, wakes the client up. The client gets the data back from the read request, and they go forward. Okay, so this is a client-server structure or paradigm. Okay, and this should be familiar to everybody, right? You're all familiar with this, like HTTP. Half of you are busy looking up websites right now, right? No, I'm just kidding. So you go to the website, you hit the response. You type it in, you hit return or enter, whatever. You wait, it comes back, it puts it up on the screen, and that's exactly what we've just done here. And so the interesting question you might ask yourself is, how do we coordinate this in a way that works? Okay. Now, are there any questions about this very basic diagram here? Yeah.
All you have is a generic file pointer. How does it know how long to wait before it declares failure?
Ah.
You have to have that information within the file structure or description.
Well, that's it. So the question is, how do we know when to give up for failure, right? That's a really interesting one. There's lots of ways to do that. One of them is we can actually set a timer that when it goes off and we've been waiting too long, we abort the request. And if you actually think about it a little bit, I mean, how do you know how long your web browser waits before it gives up? Sometimes you're like, well, why did it wait so long to give up? And other times you're like, well, that gave up too quickly, right? So the timeouts are often fixed in advance. And the time, by the way, the timeouts that you're typically seeing with the web is not necessarily this as an exclusive thing. Oftentimes the timeout you see is when you first try to resolve the address and turn it from www.something.something into an IP address, that DNS lookup is often a thing that times out and fails. So there's a lot of different timeouts in this. Yep.
How would it know between a local file and something that you're going on the network?
Oh, you mean why does writing to this go across the network as opposed to a file? Is that what your question is?
Well, I mean, like a way between different files. Is that just encapsulated within the file structure?
So what's encapsulated here, this file descriptor, once you've done the open, you've encapsulated where you're writing to or reading from in the open itself. Why don't you wait and see once I get a few more slides whether I've answered your question? It's a good question, though, I think. Okay? So, I mean, why is this going to, Europe as opposed to my local file system? It has to do with how I actually open these file descriptors on either side. Okay, and I haven't told you how to do that yet, so still magic, right? It's all magic. Poof. Okay. Any questions on this basic idea, though? We're pretty good on this. We're reading and writing from magic file descriptors, and as a result, we write to one, we read from the other, and communication happens. Okay, so far that's all I've told you. Now, in reality, of course, we said, well, these are not really files. We're putting the internet in the middle. And so when we do our write, because of the way we've set this up, the data goes into one socket, makes it to the connected other socket and comes out the other side. And here, the socket setup is actually bidirectional in this case, so the socket itself at the local endpoint is really 2 Qs going in each direction. The socket at the remote side is 2 Qs. And part of this setup process is doing this connection so that when I write in one end, it comes out the other end. Okay, and so you could view everything that goes on communication-wise with web browsing as really about how do I connect these queues up so that when my web browser makes a query, it goes to the correct server rather than some other server. Okay? Everybody with me so far? Questions? Now, all right, so basically the other thing to keep in mind, of course, is that typically this is a many-to-one kind of scenario. So many clients talk to one server. Okay, so whatever we come up with has got to handle the notion that many clients can connect with a server, and furthermore, the server's got to be able to keep track. If client 2 makes a request, better send the response that client 2 was asking for back to client 2, not to client 5. Okay? All right, think of what happened if you were doing Google searches and you got back the wrong response. That would actually probably cause some rather amusing results, but probably not what you wanted. So this is the socket abstraction. So what's a socket? It's an abstraction of network I/O queue, mechanism for interprocessor communication, and it embodies sort of one end of a communication channel. And it's the same interface regardless of where you're connecting to. So it could be the local machine, which if you have 2 processes, you can actually use sockets to communicate between the 2 of them. That's often called a Unix socket. Or it could be across the network, okay, in which case that could be a TCP/IP socket, for instance. And the sockets were first introduced in 4.2 BSD, which was a huge innovation at the time. And BSD standing for Berkeley Standard Distribution. Okay, so let's hear it for Berkeley. Okay, so Berkeley came up with sockets. All right, yay? That's right. You're at the home of some of the biggest networking innovations ever came out of here. And the data transfer is very much like files, so they're still reading and writing against a file descriptor, just like we were doing with files, okay? And it's over any kind of network. Now, you don't hear much about this anymore, but it used to be that there was all sorts of networks like AppleTalk and SNA and IPX and all of these different types of networks. They all supported sockets as well. So if you could make a connection across a network, you could put a socket abstraction on top of it, and now anybody using it could think that they're just using sockets the normal way without caring about what the transport layer was underneath. Today, pretty much, you really have kind of 2 options. You've got Unix sockets, which are local, and you've got internet sockets such as TCP/IP or UDP/IP, but usually /IP is pretty much the 2 options here for sockets. Okay, a lot of these other things have pretty much disappeared. They're still around in very select areas. Okay, so here's an echo server that you could imagine. So client gets a string, writes it to the echo server. The data goes across to the other side. It gets read from the echo server, printed out. The result is also written back. It sort of pings back. The client, which was waiting, gets its response back and prints it. So notice that all that's happened here is the client got something from the user, sent it to the server sent it back, and then the client printed it out. So that's why this is a silly echo server. Okay, the SES. Okay, so we can actually look, and by the way, then the client can do this over and over again, the server can do this over and over again, and we can do this for a long time if we feel like it. Okay, so here let's look at some code for this. So what does the client do? So the client allocates some memory and so on, and it goes ahead and gets the request from the user of the client, and then it goes through and gets the first request, and then it goes through and it writes that request to the socket file descriptor, and then it clears out some memory, and it does a read, waiting for the response to come back, and once it's got the read, it writes the response it got back to the standard output, and then it gets the next request and goes on. Okay, so we basically loop around and around waiting for the echo. And on the server, what's the server do? The server reads from its connected socket, assuming that there isn't an end sent to it or there was a failure. It takes the result, it writes it out to its own standard out, so it's getting a little local echo on the console there, and it writes it back. Here we go. You've just made your very first, or seen your very first networking echo server. Okay? Are we excited yet? Now, of course, what's missing from this is like, well, how the heck do I connect those two file descriptors up? I still haven't told you how to make the queues talk to each other. Okay, but notice that once we've got the queues properly tied together, this is very simple. This is like reading and writing files. Okay? Are there any questions on that? So we've peeled back a little of the magic, right? The thing that's still magic is, how does this sock FD talk to this consock FD and do the right thing? Okay, that's still magic, but otherwise you could build yourself a server today that looked like this. Okay? Now, of course, how do we have the prompt for the input? Well, this is boring enough that we abstracted it away, but basically we print out request : and printf with no arguments, basically just goes out to standard out, so that prints on the console, and then we do an fgetS to read from the console, and that gives us the input from the user that's going to go to the Echo server. So that's why I didn't spend a lot of time on it. And what we're going to do now is pause for station identification for about 3 minutes, and then we'll come back and we'll connect all the rest of the magic up. Actually, I'll put that one up. All right. So let's pick up. So I realize that you're still learning C and all its vagaries, so occasionally I'm going to point out a few things. For instance, what is a string in C that's sort of printable? How does that laid out? So it's laid out as a char array, right? Typically a char star points to the beginning of it. How is the end of a string often indicated? Anybody? Null character. Okay? Keep that in mind. So a null character is a character that's all, a 0 in the byte. Keep that in mind because oftentimes if you want to use a character string for something, you need to make sure that there's at least one more character in the length of memory you've set aside for the null character. Okay? And this is something that trips up a lot of early C users because they forget about the null character. And just if you're wondering why are there weird things like max request -1 or +1 or, oftentimes when there's a length and somebody adds 1 to it or subtracts 1 from it, it's because they're dealing with the fact that there's that extra character involved. Okay, so I just thought I'd point that out if you're trying to read this code after class. The other thing I'd point out is notice when we go ahead and get the request from the user, this function that we set up, getRequest, actually gave a buffer which has max in characters, and we sort of said to that function what's the maximum size of our buffer so that this function can kind of do the right thing. Now in this case, we sort of use that length in the right places to make sure we don't get a string that's too long. The other thing I wanted to point out is, string length, strlen, is a function you're going to use a lot that basically says how long is this string, and the way it figures it out is it keeps going till it runs into the 0 character. So if you were to give string length on an arbitrary piece of memory, it might overflow all sorts of stuff. So you want to make sure there's actually a 0 character there to find. Okay, end of Don't You Love C 101. Okay, so let's talk about the magic. So how do we create sockets and get a connection? So the file systems basically provided permanent objects in a structured namespace so that we could open, close, namely the file namespace. And so that was kind of easy to figure out because the files exist independent of the processes themselves. They're stored in the disk. When we get into sockets, it's a little bit trickier because sockets are kind of transient. They get set up on the fly to do the communication, and there isn't actually a file there necessarily. And so creation of these things is a little more complicated, and we want to somehow form two-way pipes between processes, and they may be, on the other side of the world, and so that's a little bit tricky to figure out, and that's where this magic comes into play. And so first of all, we have some namespaces that are not the hierarchical file namespace. We sort of mentioned host namespaces. www.eecs.berkeley.edu, for instance, is the DNS namespace for defining hosts. And there's also the IPv4 namespace, for instance, which is 4 octets or 4 bytes, typically written as written in this sort of dot notation. You've all seen this 128.32.244.172. That's an IPv4 address, 32 bits. Okay, how many bits is IPv6? 128, yeah, much bigger. Okay, that way of specifying those names is a little more complicated because there's a lot of colons and stuff. We won't go into that right now. But these IP addresses tend to represent actual machines that are specific places in the network. Okay, so that's another namespace. And by the way, typically the first thing you do when you're talking to a web service or whatever is you turn a host name into an IP address, because the host name is the more persistent thing. The IP addresses tend to change depending on various circumstances. But we need IP addresses to actually connect the sockets up. So the very first thing you're always going to do is you're going to turn your host name, which is a human-readable thing, into an IP address in order to actually connect the socket. Okay? And by the way, you should, 128.32, that's a Berkeley address, okay? In case you didn't know. Now, anybody know what the other one is? Other Class C? No, what's the other Class C for Berkeley? We have 128.32.xx.xx. What's the other one? Nah, this is too random for you guys. Why? It's just a random thing. 169.229.xx.xx. Okay. Learn something amazing for parties. I try to make sure you have a party fact for every lecture. So the other part of this namespace, which is kind of interesting and probably less known to you, everybody here has seen an IP address once before, right? How many people have never seen an IP address? Don't raise your hand. So ports, on the other hand, are a little bit different. Ports are 16-bit things, and these ports tend to be divided up into well-known ports and registered ports and sort of dynamic ports. Ports from 0 to 1023 tend to be system services, and they're well-known. What's probably the best-known port? 80. What is 80? HTTP. What's 443? HTTPS. Okay, so those are two very good ports, all right? But there's a bunch of other ones, and keep in mind that these kind of connections we're talking about are actually a combination of an IP address and a port is actually a real connection. Okay, and it's actually two IP addresses, two ports, and a protocol, but I'll get to that in a second. So here is typically a picture of the magic, okay, that we talked about earlier. And notice we've got three things that are called sockets here. We've got a server socket, and then on the client we've got a socket, and on the server we've got a socket. And this is probably my favorite diagram for how this actually works. So the web server, like at Google, sets up a socket whose only job is to accept incoming requests for connections. So that gray socket, that's its only job. Meanwhile, the client says, "Hi, I'd like a connection." The server socket picks it up, generates a brand new socket that's bound just for this one connection, and now, poof, we've got a communication two ends of the internet. Okay? So there's actually three sockets involved in what looked like a two-socket connection. All right? Keep that in mind. So the server socket basically listens for new connections, produces new sockets on each connection. So remember back we had that many to one kind of scenario. Every client makes that request, and there gets to be a unique socket connection for each client and each server. There's a unique connection. And so in this given server, it's probably got many yellow connections, many green sockets connected to many other green sockets. Okay? But each one is unique. And how is it unique? It's unique because it's got 5 unique values that make a tuple, make a connection unique. Okay, there's a client address, IP address, there's a client port, there's a server address, there's a server port, and there's a protocol. That is what makes the yellow thing unique. Okay? And when we go back to the web server kind of thing, the web server has a unique IP address. It has a unique port. We said 80. And the way that we can have many of these yellow connections that are all kept track of is each client has its own address and a port. So you could even have a client that has 3 web browsers running on your laptop that are all talking to the server, and the reason that server can keep all 3 of those web browsers separate is each web browser gets a different port. Okay, and so the client-side ports are typically randomly generated from a well-defined set of values. And that's why this unique connection isn't screwed up. Okay, it's the 5 tuple. Now, what is that protocol thing? Because I only told you about 4. What's the 5th? What's this protocol thing? Anybody want to guess? Which is what? Application level protocol. TCP is an example. UDP is an example, right? That's the protocol. So oftentimes, mostly what you guys are dealing with is a TCP IP protocol there. Okay, yeah, question.
If 2 different computers, OSs, randomly set like the same client port, like client address, can you explain like why that wouldn't be a
because they have different IP addresses. So their addresses, because the ports are only unique within a given physical server, and so yeah, those two clients could use the same random port, but they have different IP addresses, keeps it unique. That's why this 5. That's why I kind of like to point out the 5 tuple really does matter here. You need all 5, although oftentimes we're talking about the same protocol in a lot of what we're talking about. Okay? Any other questions? Yes.
If you were on a virtual machine,
Uh-huh.
you get like a predefined set of ports.
A virtual machine typically gets its own IP address and port space. It depends a huge amount on your virtual machine. Okay, and so rather than going into all the different possibilities here, I'm going to say one way to think about it is each virtual machine has a different IP address. But that's kind of a lie because there's only one physical IP address. So what really happens is the virtual machines go through a network address translation, which turns their fake IP addresses into ports in a complicated way we could go into. But for now, we'll lie to you and say, think of them as each having their own IP address. All right? And I acknowledge that's a lie, but it's a good one. All right? It's a good way to think about it for now. Good. Okay. Yeah, question? Oh, there's lots of security issues. Every security issue involving the internet is a security issue with the socket model. So, you know, I'm not going to deal with that today. We're going to have a lot of fun with this later in the term. But suffice it to say that if somebody who's a man in the middle, a third party, can somehow fake it out and make it look like they're coming from another socket, and they can get the sequence numbers in the TCP connection right, and yeah, a lot of different random stuff, then yeah, you could have somebody pretend to be either the server or the client, and that's where you start getting man-in-the-middle attacks and all sorts of stuff. Okay, so short answer, yes. Long answer, later. Good. So let's look at this server example. So the server is really going to create a server socket, bind it to its own address and port. So this would be Google binding it to the Google IP address and 80, let's say, and then goes to listen for a connection. And meanwhile, the client creates a client socket, which is not currently talking to anything, sends a connect over to the server, and what happens is that connection gets queued until the server accepts the connection, at which point now suddenly we've actually got one of those yellow connections with 2 green ends, and now the client and the server have a unique endpoint pair that they're talking with. And the server typically immediately goes into a read waiting on this particular connection. The client does a write for the request. The server comes out of read, gets to go forward to it. The client reads waiting for the response. The server writes a response. And we can keep doing this for a while, and eventually we break down the connection, we close the client socket, we close the server socket, the server goes back to wait for another connection, and we're good. Okay? So we've just set up a connection between Berkeley and Beijing, or whatever, Berkeley and London, whatever your favorite thing is. This is not a very good server. This is a bad server. What's wrong with this server? This one would annoy me. Does it annoy you? Yes. Yeah. It's busy with one client at a time. It listens for the connection. Oh, here's a connection. It goes and it handles the client. La, 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 la. And then it closes up and it goes back and gets the next client. La, 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 right? So this is a first one wins sort of scenario. So what do we want to do to this? This seems bad. Yeah. Well, we could do some hashing, but there's actually, there's a simpler problem here. Look at this control flow. This is like stuck in doing one thing at a time. How do we do more than one thing? Yeah.
When we're listening, we could also wait for the client to respond and just listen to another.
Okay, so we'd like to do more than one thing at once. What's the mechanism you have for doing more than one thing at once? Yes? Fork off a new process. Why not, right? Sounds good. And in fact, What's a little worrisome about this server is once we've gone off and started processing the client request, maybe the client figures out how to screw the server up and we don't even have any protection in this processing loop from the main part of the server. So maybe this is a little risky too. Okay? So what we could do, and by the way, this is the very simple side of the client. So the client goes through a process for turning a host name into an address, and then it creates a socket that's unbound anything. It tries to do a connect operation where it says, connect, here's my socket, which is in the raw and not connected yet. Here's the address of the remote service I want to talk to, including the port and host name are all put into this server adder structure and connected for me. And as soon as I return from connect, voila, the server, the client is now connected. So when the client goes into connect, that's one of those cases where we're pausing until we make the connection, and maybe we need a timeout. That was asked earlier if we don't actually connect. But eventually, if we successfully return from connect, then we're good to go. All right, and then the client goes and does its thing until it's done. That's what this is, and then it exits. Okay? And similarly here, the server basically creates a socket, which is a listening socket, and it binds its own address to that. And now it goes through a loop where it says, oh, listen for an incoming connection. When listen exits, what we've got is we go ahead, we know that there's somebody that's waiting, so we run an accept, where what we come out of that accept is the socket that was created for us from the server socket, which is that green one. We get our green socket. That's what accept does, and so that's why consocfd is the other end of the client's connection. And now I go ahead and use that file descriptor any way I wanted. Similarly here, this socket, this connect call returns, basically gives us the socket file descriptor, which we can go ahead and now use. Okay, basically what we did is we created the socket file descriptor, and connect will modify that socket file descriptor so that we're good to go. Okay, so we've got both ends of that connection. Okay, and that's how this works. So we already said that we want to protect the server and isolate the handling to get a little more parallelism, and so we're going to use the fork operation. And so in principle, this is what that looks like, where now the server doesn't accept by forking a child connection off, which now handles the requests with the client. Meanwhile, the parent goes ahead and waits for the next connection. Okay? And now we can handle many requests. I want to point out something interesting here, though. Do you notice the closes? Everybody see where I see close? So, notice that we're kind of closing the connection socket here and closing things. What's a little funny about forking here is that when we do a fork operation, we actually end up with the child has both the listen socket and the incoming connection. The parent has both the listen socket and the incoming connection because fork is a copy. And so the child closes the listen socket and the parent closes the connection socket because the parent doesn't need it anymore. It's handed it off to the child. Okay? Now, notice, by the way, that this particular waits for the child and goes back. So this particular fork topology here doesn't really do anything for parallelism, but it does protect the server from anything the client is doing. Okay? So somebody tell me quickly, how do we make the server now handle many requests? Yeah, stop waiting. Good, very good, right? We just don't wait, and now all of a sudden every request gets a new process. And by the way, it gets a child process that has its own unique connection, and the child process can do whatever it wants in terms of satisfying these requests. Every child process will run in parallel, and now we have a goodness to gracious, down-to-earth web server that can handle lots of requests in parallel. Okay? And so, by the way, notice in the server side, here's where we actually put the fork in here. And notice the fork basically says, gee, if I'm the parent, the first thing I do is I close the brand new green socket that I just made for that connection. Why is that okay to do? Well, because the child also got that socket, so the child goes ahead and closes the listen socket. You should think about this after class, because this is interesting, right? The fork had two sockets. It copied them both, and each of the parent and the child closes the one it doesn't need. So keep that in mind. All right, and so that gives us this concurrent server, which I show here, and basically what we did is we just removed the wait. Okay, and so here we commented out the wait, and now we've got a server protocol that works very well. Okay, and we can talk a little bit more about addresses. We're not going to do that right now, but I think we've done it. So notice we've got a bunch of big OS concepts. Woohoo! All right, why did we do it this way? We did it this way because, and this is the spiral. Dave Culler likes his spiral, okay? And I thought I would put this up. The idea here is we gave you enough of an intro of the concepts of the class so that we can actually have you do the homeworks. And now we're going to work our way out in much more detail of how these user-level ideas show up in the kernel. All right, that's where we're going. So in conclusion, you guys have gotten all sorts of good ideas now. Go forth and do homework number 1, and we'll see you on Wednesday.